Saxon Advanced Mathematics, Lesson 33. Today we are here to talk about quadrilaterals. 4 sides. This is a long, complicated lesson that has lots of geometric, philosophical details, I would say, theoretical details. We're going to skate across the top of those details and focus on the problems that are at the end of the lesson. So let's just cover the basics. Quadrilaterals, as I said, are 4-sided shapes. All right, there are 3 categories. The first one, and it's almost hard to draw because it's random. The first one has no parallel sides. Okay, sides. The second one has 1 pair of parallel sides. And well, let me finish saying something about this. We give this guy a fancy name. We call him a trapezoid. And then the third and final type of 4-sided object has 2 pairs. Oh, let me do this too. There's the pair of parallel sides, and this is 2 pairs of parallel sides. And we designate that by saying that one and that one are the same. They have the single arrowheads. And then these 2 are also parallel. And this guy has a fancy name, and that is, it's not going to fit in the space I left, parallelogram. All right, so it's important that you know there are 3 types of 4-sided shapes. The first one is random, and he doesn't have a special name. The second one has 1 pair of parallel sides. He gets to be called a trapezoid. And then the second one has matching, or parallel and parallel. And that is called a parallelogram. Now, I'm going to refer you to things in the book that we're not going to take a lot of time to discuss or to rewrite, but I want you to know where they are because you'll need some of this information to do a few problems. Properties of parallelograms. You can see it here at the bottom of the page. I'm on 233. Write that down. Just jot down page 233. Properties of parallelograms. So we're focusing in on the most particular type, I would say. Both pairs of opposite sides are congruent. Both pairs of opposite angles are congruent. The diagonals bisect each other. Any pair of consecutive angles is supplementary. That may or may not mean anything to you as I just rattle it off, but there are some questions that ask you to find the properties of, or to choose which properties of parallelograms are valid, so you may need that little chart. John also chooses to give us a little proof here that proves that opposite sides of a parallelogram are congruent. So he's proving that like B to C is congruent to A to D, which is what I just said. And AB is the same as DC. So here's a little proof. We're not going to go through that, but it's there if you ever want it or need it. And I don't think you're going to see anything like this in the homework. All right, types of parallelograms. So now we're taking this, just this type, and we're breaking it down further into 3 types. So draw this though. This is kind of it. I want you to understand the basic flow of this information and rely on the book to give you all the details. All right, so this whole box, it represents all parallelograms. All right, and I'm going to extend my box just so that that's really clear. Okay. Some parallelograms are rectangles. Some parallelograms are rhombuses. Now, as you'll recall, a rectangle has two pairs of parallel sides, but they're of different length, but they have right angles in the corners. Okay, that's what a rectangle looks like. A rhombus is a squished square, if you will. Okay, let me say this. Rectangles have two pairs of matching sides. A rhombus, everything is the same length, but they don't have right angles. And so what is at the intersection of these two are squares. Because they're a combination of both, aren't they? They have the right angles and they have the equal sides. So this helps you understand how all these shapes relate to each other, right? Quadrilaterals, the no-name randos, the trapezoids, we're going to come back to them. Right now we're talking about the parallelograms. Within the family of parallelograms, we have rectangles, rhombuses, and where they intersect, we have squares. I just feel like coloring that in because John did in the book and it looks really cute and I just want to kind of make it darker. All right, now, each of these three groups has some interesting properties. As you can imagine, there's overlap between them, but then they have distinct properties too. Here's another place in the book that you'll want to mention. Let's see. This was page 233, where we first talked about the properties of parallelograms. Now on page 235, we get specific properties of rectangles, rhombusi, and squares. And let me just show you where they are. Right here, okay? There's a picture of each type. When we talk about diagonals, we mean these dotted lines, okay? I don't want to drag you down right now. We're skating across the top, right? But there are details here that talk about specific properties of rectangles, specific properties of rhombuses. And then look, when we get to squares, it says all the properties of a rectangle apply, all the properties of a rhombus apply. The diagonals form four congruent right angles. So there's one bonus fact, right? They make these cute little isosceles triangles. So John is going to ask a few questions along the way, like example 33.2. The diagonals of a certain parallelogram are of unequal length. Which of the following could the parallelogram be? Now you can read through these details and that will help you, but here's an easy way to answer that question. We're looking at the diagonals and whether or not they're the same. Well, you can look at this and go, yeah, those look the same. And in a square, yeah, those look the same, but look at in a rhombus, this one's definitely longer than this one, right? So we can say, oh, it's the rhombus that has the unequal diagonals, and sure enough, that's the right answer. So, kind of intuitive, you guys. That's why I don't want you to hurt yourself on these. Now, oh, and here's one more. The diagonals of a certain parallelogram are not perpendicular. Which of the following could it be? Rectangle, rhombus, or square? They're not perpendicular, so let's go back and look at this chart. Perpendicular meaning they meet at a right angle. As we look at the rectangle, we go, yeah, those definitely are not meeting at a right angle, are they? But these look pretty good, don't they? These look like the diagonals meet at a right angle. And there it is, number 3. The diagonals are perpendicular. And then when we go to the square, they look pretty square too, don't they? And then we realize all the properties of a rhombus applies to this, so the diagonals would be perpendicular here. So with just a little bit of looking through this, we see common sense descriptions that are pretty easy to interpret. And we can see, oh, this is the guy who doesn't make right angles, right? These two do. He definitely does not make a right angle with his diagonals. And so the answer, the one that has not perpendicular diagonals would be the rectangle. And John showed us a picture. Okay, now John backs up a little bit and he talks to us about parallelograms. What makes a quadrilateral a parallelogram? So now he's going back and he's talking about what's going on here, conditions for a parallelogram. And so this is more information on page 236 that will help you determine whether your four-sided object is indeed a parallelogram. And they're basic, you guys. They're so simple that it's confusing almost, right? Both pairs of opposite sides are congruent. One pair of opposite sides is... I don't even want to read it because it's confusing because it's so kind of stating the obvious over and over. But I just want you to know there are two charts that talk about qualities of parallelograms, and then on page 235 is where you get the information about these three. I believe there are some questions about this in the homework. And I think you can figure them out using that information on 235. Now what I want to do is switch the conversation. And we're not going to do any calculation problems on this. I don't think there are any in the homework. Correct me if I'm wrong when you video chat with me, but now we're going to go and talk about the trapezoid, one pair of parallel sides, and this is where we're going to do a little bit of calculation work. And we're almost to that. Okay, so trapezoids. They have one pair of parallel sides. So that's usually how they're drawn, is we make the top and the bottom be parallel. And they don't have to be the same length because these guys are not parallel. If we made them the same length, then the other sides would be parallel and we'd have a parallelogram. All right. One pair of parallel sides. And we can divide a trapezoid down the middle. And we call that the median. And we usually call this, like the first base and this the second base, which is a little confusing. But a cool thing about trapezoids is that if we take the two bases and average them, right, add them together and divide by 2, that will equal the base. So the median equals the average of base 1 and base 2. All right, that comes in handy when we want to do problems. I don't want to talk about that. On bottom of page 237, there's a little chart that says properties of a trapezoid. It has this fact that we just said. And the other fact we're going to look at in just a minute. Let's start with the examples. Somehow we jumped all the way up to number 5, so that's cool, right? Derive a formula for the area of a trapezoid using the figure shown. Okay, we can do this. It sounds hard, but it's not. And this is where trapezoids become kind of fun and very non-threatening. Okay, so here are our parallel sides. We know it's a trapezoid. It has one pair of parallel sides. And we're given this measure, and we're told that it's h. So we're not getting numbers, we're getting letters that describe this. And just like I talked about here with the base 1 and base 2, John puts base 1 on the bottom and base 2 on the top and calls them B. Doesn't matter, that's fine. And so how do we write a formula to show how to find the area of this? Well, here's what we're going to do. We're going to divide this into 2 triangles. And we're going to call this area 1 and we'll call this area 2. All right? So let's find the area of this first part. Area 1 equals, let's see, it's base times height divided by 2 for a triangle, right? Because I've just made a nice little triangle here. So base 1 times the height divided by 2 is area 1. Area 2 is, look, the base is up here, right? That's kind of weird, but it's easy enough to see. Oh, if we take that point and lift it up, then this would be standing on its base. So this is going to be base 2 times the same height. It's upside down, but it's still h, divided by 2. So if we add these two to get a formula, area 1 plus area 2 equals right? And we can factor out, let's see, this is a 1. We can't factor out the b's, but we can factor out h over 2. And then what we'll have left is base 1 plus base 2. So the area of a trapezoid has a formula. It's the height divided by 2 times the first base plus the second base. And another way to write this is to just pull the fraction out separately and say it's 1/2 h times b1 plus b2. All right? So here's the formula. We just figured it out. And you can write this in your book. What I would do is I would not write that part. That's kind of like an algebraic mid-step. This is probably the cleanest version of the formula. But here's the thing. Anytime you want to find the area of a trapezoid, rather than trying to remember this freaking formula, just make 2 triangles out of it and find the area of each triangle. This works every time and it makes trapezoids so easy. Let's try another problem. There are a total of 2 more? Yes, 2 more problems and then we're done. Example 33.6. The figure shown is a trapezoid whose area is 175 centimeters squared. Find x. All right, this is what it looks like. There's a wonky side. There's 2 sides that are parallel, clearly, even though one's way longer than the other. And then this connects. We're told this is x, and we're told this is 2x plus 8. And then we're told this is 10. Now, there's 2, dimensions are in centimeters. There are 2 ways to do this. The way that I consider the harder way is to go back, grab our formula, and set it up. We know the area of the whole trapezoid equals 175, right? Let me just double check. Yeah, that's right. So we could plug in these values. Let's just do it. Let's just do it. I want you to see that it works. And then we'll do it the other way, which I think is the easier way, where we'll just make triangles. So our formula is that the area equals 1/2 times the height times the first base plus the second base. So this is our first base, this is our second base, there's our height, and there's our area. Let's plug in what we know. And we're solving for x, so that should fall out in the algebra. So 175 equals 1/2 times the height, which is 10, times x plus 2x plus 8, right? There's base 1 and there's base 2. All right, that looks pretty good. Let's cancel those two against each other and combine like terms and see where we're at. 175 equals 5 times 3x plus 8. This is just basic algebra, right? Let's distribute. 175 equals 15x plus 40. How does that sound? Yes. We'll subtract 40 from both sides. 135 equals 15x. And then what do you suppose that simplifies to? That goes up. Well, what I notice is that if we add 15 more to this, it would be 150, and then it would reduce to 10. So I'm guessing this is going to reduce to 9. Let's just try 15 times 9 and see what we get. 135, yep. So x equals 9. Remember that in a problem like this, 9 does, well, it does represent the length of this one because it's plane x. So this length is 9, and this one would be 2 times 9, 18 plus 8, so this would be 26. John does not ask us to find the length of the parallel sides. John asks us to solve for x. So we've done it. So this is our first way of approaching this problem, and this is by using the formula. All right, and I'm just going to divide that off. Over here, we're going to do it the other way, and we're going to forget about the formula, and we're just going to do it by triangles. Okay, so I'm going to divide like this. There's one base, there's the other base, and there's the height. So I know that if I find the area of this triangle, A1 equals the base is x times the height is 10 divided by 2, and add it to the base of the second, or the area of the second triangle, which is 2x plus 8 times 10, right? That's the height again. Base times height divided by 2. If I simplify these, add them together, and solve, I should get the same answer. So I'm going to simplify before I add them. This is 5x. This, I'm going to distribute 5 rather than the 2, or the 10 rather, because I'm going to divide it first. I can cancel these because while I'm adding here, the 10 is actually being multiplied. So I'm good to, it's already been factored out. Okay, so then this becomes 10x plus 40. Now I can add together A1 plus A2 equals, and now I need to add this and this. So that will be 5x plus 10x plus 40, and I can substitute in that the total area is 175 equals 15x plus 40, and look, we're at the same place, right? We're right here. Here's where our two strategies come together. Subtract the 40. 135 equals 15x, divide by 15. X equals 9, just like last time. All right, so these two strategies both work. This one you have to remember the formula, and this one you don't. Right? It's just that simple. Okay, so this is what I like about doing trapezoid problems, is they're fun and easy. Parallelograms, by the way, work the same way in that you can just divide the parallelogram into two areas and find the areas independently. All right, last one is a slightly different jam. In the figure shown, let me draw it so you can see it. Letters A, B, C, D, E, and F. And look, they all have these horrible expressions for their length. Okay, in the figure shown, segment EF is the median of trapezoid ABCD. Find X. Okay, so somehow we have to use all of these to try to set up some sort of equation that will allow us to solve for X. Do you remember what I told you a few minutes ago about the median? And that is that the length of this segment is equal to the average of those two. So here's how we can write the equation. The middle one, the median, 4x plus 1 equals the top plus the bottom divided by 2. 2x plus 2 plus 7x minus 2, all of that over 2. Right? The length of the median, that's the length, right, the segment, equals the top plus the bottom divided by 2. I just wrote that on 2 lines because I knew I couldn't squish it all up there. All right? That lines means the segment or the segment length. Okay, so that's what we've done, right? The median equals the top plus the bottom divided by 2. Now all we have to do is algebra. I want to get rid of this denominator. I'm going to do that by multiplying both sides by 2 using the second rule of algebra. This one I have to distribute. This one cancels. So I get 8x plus 2 equals, and now I'm going to combine like terms. And look, I'm going to get 9x, but these guys are going to cancel, aren't they? So I'm just going to get 8x plus 2 equals 9x. I'm going to subtract the 8x. We aren't even going to have a best friend this time, are we? 2 equals x. Yay! In this case, our answer is algebraic. I have not been putting smiley faces. All our answers were correct. In this case, I did not find the length of any of these segments. I found the algebraic answer. If we wanted to find the length of any of these segments, we would plug it back in, right? And if x equals 2, then this would be 6, and this would be 9, and this would be, what, 14 minus 2, this would be 12. So that's another fun way John can take this content and come up with a pretty straightforward and not that difficult problem. These last 3 examples are what I want you to take away from this lesson. I also want you to know that there's a bunch of picky details. I want you to remember that there are 3 different kinds of quadrilaterals. No parallel sides, 1 pair, 2 pairs. Fancy names for the ones with the pairs, trapezoid and parallelogram. Parallelogram is made up of these 3 shapes, and there's all kinds of little properties. Trapezoids are fun to do problems with, okay? That's what I want you to remember about good old lesson 33, and I will see you next time for 34.